Evaluating limits of trigonometric functions using identities. Alright, so first let's go in and let's review what our basic trig identities are. More specifically, our quotient identities and our reciprocal identities. So our quotient identities, our first one is tangent, and hopefully remember that tangent is equal to sine of x over cosine of x. And our second quotient identity is cotangent of x, which is cosine of x over sine of x. And these are quotient identities because we are taking the quotient of two trig functions. Then for our reciprocal identities, we have the cosecant of x is equal to 1 over sine of x. We have sine of x is equal to, secant of x is equal to 1 over cosine of x. And cotangent is equal to 1 over tangent of x. So these would be the reciprocal identities because they're 1 over a trig function. And the one thing to mention here is that notice how we have cotangent of x is equal to cosine over sine, and cotangent of x is equal to 1 over tangent. Both these identities are 100% accurate, but sometimes it just makes more sense to use one instead of the other. So use when appropriate. So the first limit we're going to be looking at is the limit as x approaches 0 of tangent of 7x over sine of 5x. And as always, it's good to just do direct substitution just in case. So we're going to get tangent of 7 times 0 all over sine of 5 times 0, which is going to give us tangent of 0 over sine of 0, which will be 0 over 0. And up until now, we have said 0 over 0 means we need to factor and cancel, but unfortunately with some of these trig identities, factoring isn't possible, so therefore we can't factor and cancel. So this is where we need to apply our trig identities. And the first one we're going to look at is tangent. So I'm going to rewrite this limit. So we're going to have the limit as x approaches 0 of tangent of 7x over sine of 5x can be rewritten as the limit as x approaches 0 of sine of 7x over cosine of 7x all over sine of 5x. Because let's remember, tangent is equal to sine over cosine. And now it's like, we seem to be stuck again because there's nothing that we can cancel out or simplify. But if we remember our special identities for limits, we know we have a limit as x approaches 0 of sine of ax over sine of bx is equal to a over b. And we can see we have a sine in the numerator and we have a sine in the denominator. So if we can somehow move that cosine of 7x out of that fraction, we might be able to apply this identity. So that's what we're going to try to do. So I can rewrite this limit as the limit as x approaches 0. And yes, we need to keep writing the limit symbol until we apply direct substitution or one of our trig limit identities. So I'm going to rewrite our expression as sine of 7x times 1 over cosine of 7x all over sine of 5x. So I basically just broke apart the fraction that was in the numerator. Alright, so let's see, we got the sine of 7x to be free from the cosine, but that cosine of 7x is still hanging around. So I need to continue to rewrite this. So I can rewrite it as sine of 7x over sine of 5x times 1 over cosine of 7x over 1. So now I've been able to pull that cosine of 7x out, and that's going to leave us with something that matches our identity. Except first, we have to put this 1 over cosine of 7x into its own limit. And fortunately, we know that when we have multiplication, we can pull apart the limits into two separate limits. So I can rewrite this as the limit as x approaches 0 of sine of 7x over sine of 5x times, And 1 over cosine of 7x over 1 is the same as 1 over, oops, I forgot to break it apart into the two limits, excuse me. So it'll be times the limit as x approaches 0 of 1 over just cosine of 7x, because dividing by 1 doesn't change anything. Now, our first limit matches our identity. So we can come in and we can say that this first limit is going to be equal to a over b, or in this case, 7 over 5, times, for our second limit, there's no identity to match 1 over cosine of 7x, so we'll just use direct substitution. And that's going to give us 1 over cosine of 7 times 0. So we can simplify this to be 7/5 times 1 over cosine of 0. And if we remember back to pre-calculus, cosine of 0 is equal to 1. And 7/5 times 1 over 1 is just going to be 7/5. So for this particular problem, we had to use our quotient identity as well as one of our identities for limits of trig functions here. So it's all about combining the tools that we have in order to get an answer. All right, let's take a look at another example. Here, we want to evaluate the limit as x approaches 0 of 4x over tangent of x. And again, it's always a good idea to try direct substitution just to see what happens. So we're going to get 4 times 0 over tangent of 0, which is going to be 0 over 0. So, again, with trig functions, there's nothing we can really factor or cancel here. So we have to go back to our identities, and I know that I can rewrite tangent as sine over cosine. So I'll come in here, and this is going to become the limit as x approaches 0 of 4, oops, that's the highlighter, of 4x over sine of x over cosine of x. Now it's just like, is that really helpful? And in a way it is, because we do have that special limit, the limit as x approaches 0, of x over sine of ax equals 1 over a. In this case, we do have an x in the numerator, and we do have a sine in the denominator. So we just need to get rid of the 4 and the cosine, and then we can apply that special limit. So I'm going to start pulling apart this function, so I can rewrite this as being the limit as x approaches 0 of 4 over 1 times x over sine of x times 1 over cosine of x. All right, 4 over 1 is just 4, and it is a coefficient, so I can pull it outside the limit. So this is going to be 4 times the limit as x approaches 0. And then I'm going to pull apart this fraction a little bit more to get x over sine of x times 1 over cosine of x. All right, so now we do have the x over sine of x like we wanted, so that's good. But we still need to get this 1 over cosine into its own limit. And since we can pull apart multiplication into its own limits, we can do that now. So we're going to have 4 times the limit as x approaches 0 of x over sine of x times the limit as x approaches 0. And as luck would have it, 1 over cosine of x is just cosine of x. So quickly, let's take a look at that. So we have 1 over cosine of x. Well, that can be rewritten as 1 divided by 1 over cosine of x. Remember, when we're dividing a fraction, we can change the division into multiplication as long as we flip the second fraction, which becomes cosine of x. And then 1 times cosine of x is just cosine of x. So that's how we get just the cosine. And now we can start evaluating. So we can get 4 times, well, for x over sine of x, we can use our identity. We can see that our a value here is 1. So therefore, the limit as x approaches 0 of x over sine of 1x is going to be 1 over 1. times, and then we can just do direct substitution for our second limit. So this is going to be cosine of 0. Well, 4 times 1 over 1 is just 4. Cosine of 0 is 1, so therefore this limit is equal to 4. Next up, we're going to take a look at evaluating the limit as x approaches 0 of 4x times cosecant of 7x. Now, again, we can always try to do direct substitution, and this is going to give us 4 times 0 times cosecant of 7 times 0, which can be simplified to be 0 times cosecant of 0. But the problem is, cosecant of 0 is undefined, so we actually can't even evaluate this to figure out if it's 0 over 0 or something else. So direct substitution is a complete failure there. But based on our trig identities, we know that we can rewrite cosecant as being 1 over sine. So that's what we're going to do next. So we're going to take the limit as x approaches 0 of 4x times cosecant of 7x, and we're going to rewrite it as the limit as x approaches 0 of 4x times 1 over sine of 7x. And I misjudged my room, so I'm just going to move this down a little bit here. All right, well, now I have 4x times 1 over sine of 7x, so I can even rewrite this as one single fraction, as being 4x over sine of 7x. And this looks really familiar, because let's remember we have that same identity, the limit, as x approaches 0 of x over sine of ax is equal to 1 over a. And we can see here that a is 7, but before we can apply this limit, we need to get rid of that 4. And so since that 4 will eventually become a coefficient, I can just take this 4 and pull it outside the limit to give ourselves 4 times the limit as x approaches 0 of x over sine of 7x. And we said since a is 7, we can apply our special limit. So this is going to give us 4 times 1 over 7, which will give us an answer of 4 sevenths. And our final example here, we have the limit as x approaches 0 of cosecant of 4x all over cosecant of 6x. All right, so if we did do direct substitution here, we would get cosecant of 0 over cosecant of 0. And like we said in the previous example, cosecant of 0 is undefined. So therefore, direct substitution won't work here. But similarly to the last problem, we know that cosecant can be rewritten as 1 over sine. So that's our first step here. So we're going to have the limit as x approaches 0 of 1 over sine of 4x over 1 over sine of 6x. And woo, complex fraction. Fraction in the numerator, fraction in the denominator. All right, so we don't really like complex fractions, so if we can get rid of the complex fraction somehow, that would be awesome. So I'm going to do a little bit of sneaky math here that I demonstrated on the last slide. So here we have 1 over sine of 4x divided by 1 over sine of 6x. So I'm going to write it just like that. 1 over sine of 4x, but instead of using the fraction, I'm going to use the division symbol and have 1 over sine of 6x. And then if we remember to fraction division, if we change the division to multiplication, we need to flip that second fraction to the reciprocal. So this is going to be 1 over sine of 4x times sine of 6x over 1. And since we're multiplying fractions, tops go with tops, bottoms go with bottoms. So this is going to give us the new limit, the limit as x approaches 0 of sine of 6x over sine of 4x. And this matches our special limit, the limit as x approaches 0 of sine of ax over sine of bx is equal to a over b. So in this limit, we can see that a is 6, b is 4. Let's double check to make sure our limit approaches 0, which it does. So therefore, our answer is just going to be 6 over 4, which can be simplified down to be 3 halves.